All right. So there is homework coming up due on the 30th. And the homework is, if we give you an unknown program, obviously a compiled ELF file, because that's what we've been working with all along. And if we assume that libc start main is going to be called, then we should expect RDI to hold the address of main at the point that it's called for the reasons we've discussed previously. We went through this in lecture 8, I think it was. There's a whole section on how Linux or how the C runtime starts main, how it finds and starts main. And so, we went through that and how the RDI holds the first argument to libc start main, which happens to be the address of main. And so the trick is, can we write code that does that? And we can. I promise you, it can be done. So given an ELF binary executable, locate the entry point and disassemble the basic block starting at that address. So that shouldn't be a terrible thing to do, right? You know how to open up an ELF binary already. You've already done that. And if you haven't, you have my code that does it. And you can find the entry point. The entry point is located in the header, and ELF file gives you access to that information. So you can grab the ELF file and grab the header, and then look for, I think it's E_entry, and that'll give you the address of the entry point. Now, the entry point address is not the same as the address of the start of the text section. Okay, we're going to assume, right or wrong, that the entry point is located in the text section. As we've seen in class, it doesn't have to be, but we're just going to simplify your life by assuming that the entry point is in the text section, or it's not there. So go to get the sections. You know how to get sections, and start disassembling at the entry point. Now, the trick to start disassembling at the entry point is to recognize that the address of the start of the text section is not necessarily the same as the address of the entry point. And you should be sure that the entry point is actually located in the text section, because there's no guarantee that it will be. In fact, there are some compilers that explicitly put it somewhere else. So you should check that, right? You know the address at the start of the text section. You can get that from the section information. And you know how long it is. You can just ask for the length of the data array, or you can there's an actual property in the header for the section that will tell you. And so it starts at this address, it's this long, that must be the address range, and you can figure out if the entry point is in that range. The other trick is you have to start disassembling at the entry point, which isn't necessarily the first byte of data, but that's okay, because you know how arrays work, and Python provides array slicing. So you can calculate the correct slice of the array that would let you start disassembly at the entry point. Right? Nothing too tricky or magical about that. I don't think that there is. So that'll get you the disassembling at the entry point, and you know how to end a basic block. Basic blocks end when you have a branch or a jump or a halt or a return, and so you can just run the disassembly till you find one of those. Now, here's the second bullet. If you find a call followed by a halt, then we can assume that RDI, by the time you reach that point, holds the address of main. If you don't find that, if you don't find a call followed by a halt, it's entirely possible that you don't have a main and you should give up, right? So like the second example over on the right, can't locate main, so give up. So if you don't find a call followed by a halt, you should call it a day. So what you're going to have to do then is look in the basic block and find out where RDI is being set. And there are basically, there's a myriad ways to set RDI. And short of emulating the program, you're going to have to do a a heuristic, sort of a best guess at how it gets set. And the most obvious ways are going to be an address is moved into it. So a move RDI with some fixed address, which does happen on the platform. The old Python used to be compiled that way until very recently. Or with an LEA, load effective address, which is the most likely thing that you'll find. And there are two different ways that load effective address can show up. It could show up with just a displacement, which basically loads an absolute address in. This is so rare, I'm going to go ahead and say it's not going to happen. I do not expect to see that. I just don't. So you probably won't see that. And so if you don't handle that, I'm fine with it. If you want to handle that, that's great too. Or you'll see the address of RDI set by an RIP relative address, which is the most likely thing that you'll see. And so in that case, it'll be RIP plus some offset. And of course, the offset could be positive or negative, depending. And so you'll have to look and see how you can get the offset from the operand element and figure that out. It's not very hard. Okay, so and you already know how to compute where an RIP relative address goes. We've covered that many times. And so then you'll know the address of main. So those basically the two things you should look for are moving an address into main and then using an RIP relative address and loading that address into RDI. So compute that address. And if you can't find if the basic block doesn't look right, doesn't end the correct way, or you can't figure out what the address is, then just give up and say cannot locate main. That'll be sufficient. Call your program main.py. The output should look identical to what you see over on the right, unless, of course, there are errors, in which case you should use the error library to generate an error. Some hints. Don't try to parse the text of the disassembly. The Capstone library is there to provide you with services to help you with that. It may not be the most super intuitive, but it's there and it works. And there's a little bit of online documentation, like I mentioned previously, and also in an email recently. And also there's the Python documentation that you can browse. RIP relative addressing. Assume instructions you want to be in the text section, but handle the usual errors. The file might not be found. It might not be an ELF file, and there might not be a text section. I don't expect to get big stack dumps from this. You should just be able to handle that and generate an error. Just basic programming. Some of you asked about finding the operands, and to get that, you need to turn on details. I sent out an email about that. That was actually in the online documentation for Capstone, but just set details to true, and then you'll have an operand array. Watch for prefixes in the mnemonic. Now, I don't really, I mentioned this, but I'm not going to test your code with any examples of this. If you poke around in the system, you can probably find some cases where instead of a call, you'll see like a mem32 call. So you see something with a prefix in front of it. And don't worry about that. I'm not going to worry too much about that. But when you get back the mnemonic from Capstone, if there are prefixes, it includes the prefixes in the mnemonic. So it won't exactly match call. The way to do that is to extract the last word. And an easy way to do that in Python is with the code you see there. If inst is your instruction, grab the mnemonic, split it into words, and then take the last word. But again, if you don't have to do that, that's not necessary. I'm not going to test your code with anything that would cause it to fail for that. Whew. All right. Before I go on into tools, are there questions about the homework?
Yes.
Sure.
Where can we actually find an ELF file to test on? Because I'm not certain if there's a specific ELF file you've given us to download to try on, or if we're just supposed to find one in our system.
Just about everything on your system that's executable is an ELF file. If you want to know for sure, just use file and the name of the thing, and it'll tell you if it's an ELF file or not. For example, user bin bash, the bash shell is an ELF file. ls, who, basically any executable on a Linux system other than a shell script or a Python script, other than scripts, is going to be an ELF file. That makes sense?
So you said just like, what did you say? Like,
So any executable on your Linux system other than a script is going to be an ELF file. So user bin ls. So in fact, user bin is full of stuff. Anything that you compile. So if you write a hello world program and compile it, the compiled version of it is an ELF file. Anything that we've been working on with assembly over the course of the class, those are all ELF files. Any executable binary file on your Linux system that's not a script is going to be an ELF file.
By script, you mean just the raw text file? You mean so like if it was assembly thing, it'd be like the actual, would it be the actual .o?
Yeah, so the .o is an ELF file, and then the thing that you finally, the fully linked version is also an ELF file.
All right, thank you.
And libraries. So if you can find like glibc.so, that's an ELF file. So if you find libraries in userlib, those are ELF files as well. They probably are a good thing to test with because they're an example of an ELF file that doesn't have a main.
Did you say user/lib.bin?
Yeah, user bin. I would look in user bin.
Okay, thank you.
And basically, any command that you're running at the prompt, Python, when you type Python and run Python, the Python executable is an ELF file. And, it has a main, I believe. So you could test it with that.
Say again, please.
Oh, I said the Python executable is an ELF file. So if you do a which Python, it'll show you what it is. And it's probably in user bin Python, if I had to guess. And that's an ELF file.
Mm-hmm.
So yeah, any executable on your system is going to end up being an ELF file or a script, or I guess maybe a symlink to the actual file. Python maybe a symlink to Python 3, but the actual thing itself is going to be an ELF executable.
Yeah, I actually tried to do like, I tried to run the Python script on itself to see if we could check if it itself was an ELF file, and it didn't work. It told me that it didn't have a magic number. So.
So let's try this. Here's my main solution, and if I run it on something that's not an ELF file at all, like I don't know, main.py, right? That's not an ELF file. That's a Python script, and it's going to tell me the magic number doesn't match. Okay,
right.
That's what I expect to see there. But if I run it on something else, like I go and find ls and put the path to ls in there, which is probably user bin ls, then it's going to tell me, okay, here's where main is. It's at 4E00.
What is that specific command you're doing there? Which ls?
So which ls tells me where a particular command is located on the system. So if I type who, that's a command that runs on my system. And if I type which who, that tells me where it's located. And so user bin who is an ELF executable. So when I run it with file, I will see that here it is, and it's a 64-bit ELF executable, compiled for x86 64, dynamically linked, etc. So it's located at this location. And when I want to when I don't want to spend time looking it up and then pasting that in, I can use this trick right here, which is a bash thing, which will put the result of this command right here. It will replace this result of that command. Another way to do that people probably may be more familiar with is doing it this way, putting it in backticks, and that'll do it as well. So another good thing to point out is once I have this value right here, is that right? How would I check that? Well, I can go ahead and open it up in the open up the disassembly of it, and I can look for 4E00. And there it is. And a pretty good hint that I'm on the right path is that it begins with this branch protection, this branch target protection thing. That's a pretty good hint. I could also look for start, but I won't find it, right? Because it's not going to be in here. Now, if I build a piece of code, if I want to test it with my own code, and I have a whole bunch of assembly lying around here, I could test it with some of my assembled stuff. So here's a hello world, and this has a main. And so if I make it and build it, and then I could try my little piece of code with it, right? I could go back up and do this with hello main, and it'll give me a result. It'll say, okay, main is at 1140.
Okay.
And I can check that. And 1140, sure enough, look at there's main. So it worked, hooray. And it got it because it went in and found start. Let's see if we can find start ourselves. There's start right here. So here is the basic block plus some more that begins at start. So I could come in, I could walk through. The basic block is terminated by the halt. There's a call immediately prior to it. So that's the pattern I'm looking for. And then I can look for where RDI is set, and it happens to be right here. And it's set with an LEA, and it's set to RIP plus 0xD1. So what is the actual address for that? Well, it's the address that starts the next instruction, 106F, plus the offset, which is D1. So F plus 1 is 10. So in hex, so we'd make that 7, and then we would add this 13 to it, which would be 20, which is 16 plus 4, which is 1, 4, so 140. So we'd end up with and the one here, 1140, which is it. Okay, good, yay, math still works. So you would just basically take the offset here, which you can get as an actual int in Python, and add the address of the next instruction. How would I get the address of the next instruction? Well, if I know this address, I know the address of the instruction I'm looking at right now, and I know how many bytes it is, and in fact, you can find that in the instruction. The instruction's length in raw bytes will be there. I could just add that to this and get this number down here, and then I would add the offset, and I'm in good shape. So that would work, and that'll give you the address of main, and that's what we're looking for. And if that pattern is not there, or you can't figure out what it is, then just tell me you can't figure it out, and that's what we're looking for. All right, other questions about the homework? All right, good deal. So let's talk about tools. So I had a great tool for you today, and pretty excited about it because it's one I really like. It's up and running on the computer that's not plugged in because my office is still torn up, so I can't be in there. So I'm in the kitchen today. So a lot of coding from the island in the kitchen. But the tool is PyRebox, and I really think this is a really cool tool. Basically, what someone did was take QEMU, which is an emulator, and modify it so that there is a Python instance running. And you can run programs in this, you install an operating system and do other stuff. QEMU is basically like VirtualBox or VMware in a sense. You can install stuff under it, and then while the computer is running, while the QEMU emulated computer is running, you can interact with it through Python and do all kinds of cool stuff. And I think that's really neat. You can trace into the OS, trace into the kernel, modify register values, and so on. It's pretty fun. And so I reproduced the instructions to install it because they're not necessarily super obvious. And when I did that, I hit a glitch. The glitch was there's a problem with it right now, which has not been patched in the distributed code, but there is a patch for it up in their build. So okay, fine. So there's a patch on GitHub. Grab the patch, apply that to these two files. Great. So now we can build it, except we can't because there's a problem with the bundled version of QEMU that won't build on Ubuntu and some of the Debians. Okay, fine. So I went down the road of looking at that and trying to get it to build, and it's a little tricky. So I gave up. So as a result, we don't have I was going to demonstrate it for you on the other machine, but the other machine is unplugged in the other room. So sadly, no Pi box for you. But we'll revisit this once the problems get revised and are solved, and hopefully we'll get to look at it. It's a really neat little tool. All right, so let's talk a little bit more about some fun assembly topics. Everybody loves assembly. How do I set a register to 0? So you already know some of this, right? You know that I can do stuff like XOR the register with itself. And you'll see that in code when someone wants to set a register to 0. You'll also sometimes see this, sub EAX EAX, just because that's what you'll see. I did a search, but I didn't put the results in here over my system, and I found a few thousand files which contained this command. So whether zeroing it out by subtracting a register from itself. So why are those so popular? Well, whoops, how did that happen? They're popular because, so up here we have a little assembly file. And I strongly encourage you all to just play with this stuff, right? I can throw some commands in a file and build it. That's a super low cost thing to do for me to experiment with this. And in a modern operating system, you're going to be protected against bringing the entire machine down. So just write some assembly code, throw it in a file, and see what happens. Right? I expect you to be playing with this stuff. So I'd make that, and then I would do an obj dump on it, and both the XOR version and the sub version come down to just 2 bytes. So there you go. So this is one way of setting it to 0, another way of setting EAX to 0. And because I'm setting EAX to 0, the 32-bit view of it, I'm also setting the 64-bit view, right? If I set the 32-bit alias to 0, the low 32 bits, it's automatically 0 extended into the high 32 bits. If I set the low 16 bits or the low 8 bits, it is not. So just keep that in mind. All these set RAX, the 64-bit register, to 0. The downside to these, if you want to worry about that, is they set flags. These operations will set the flags, and maybe you don't want to do that. Sometimes it's really important that you set something to 0 without modifying the flags. And we can, in fact, do that. There are some clever ways to do that, and maybe some less clever ways to do it. One is to just straight up move 0 into EAX, right? We'll fall back to the actual instruction that's supposed to be used to put a number in a register. So there you go. If we do that, we need 5 bytes, and they look like this. And this is the listing file, by the way, produced with this little -L. So here are the 5 bytes. B8 is the single byte for the move opcode, and then you have 1, 2, 3, 4 bytes for a 32-bit version of 0, which is what you're putting in EAX. All right. Well, that's 5 bytes. We can get down to 4 bytes if we do it this way. Now, here's the XOR thing, which I've already told you modifies the flags. That's not what we want. We want to do this without modifying the flags. We say so over here in the text. So before we do it, we push the flags, and after we do it, we pop the flags. So we save the flags, we do the XOR, and then we restore the flags. And I've seen this in code as well. And that looks like this. 9C is push, 9D is pop, and then the 31C0, that is our little 2-byte exclusive OR that we saw on the previous slide. So a total of 4 bytes. So we've shaved off 1 byte to get this. There we go. Pretty good. The best way that I know to set a register to 0 without modifying any flags is to do it this way, to do a push 0 and then pop RAX. And you might think the push 0, that's got to use up at least 4 bytes or maybe 8 bytes, but it doesn't. It turns out pushing 0 is a 2-byte thing. And this actually pushes a 64-bit 0 onto the stack, because of course it does, because nothing in assembly makes sense. So that pushes an 8-byte or 64-bit 0 onto the stack, and then this pops it off, and that will do it. And I've seen this used in a variety of places. I actually came across this and scarfed it up from a piece of malware I was looking at, where they had some flags that they'd set way up somewhere high in the program, and they were doing a ton of operations that didn't modify those flags. So then they could surprise you with the branch at the end and how it was taken. It's an giant opaque predicate. So, there you go. So what is the point of this? Why am I telling you all this about setting a register to 0? It's because you're going to see, if you get into reverse engineering of code, you're going to see weird little idioms like this, and you're going to have to, take a look at it and say, what's really going on here? Why are they doing it this way? Or what's the point of pushing a 0 and then popping it when I could just XOR it with itself, right? I mean, they're both sort of weird to look at, but why am I doing the 3-byte thing and not the 2-byte thing? It must be the flags. And so, that tells me, especially with a piece of malware, that they made an intentional choice to do something to preserve the flags, which indicates to me that the flags might be important and that this might be an opaque predicate that I'm looking at. So all these little things constitute hints to you as the analyst, or to your code that's trying to do the analysis, as to what's going on, and something you might take a look at and think about a little bit. All right, enough of that. By now, you should be able to set any register to 0 with any number of bytes, just about. Let's talk about lookup tables. So lookup tables are maybe less common than they used to be, but they're still there in the code. So it's a pretty common operation, it turns out, that you want to map 1 byte to a different byte. That shows up in a lot of different contexts. And a way to do that would be to use a lookup table. So down here at this location, we have a little tiny lookup table, right? This tells us which hex digit to use. And if you want to know which one to use for, let's say 12, well, here's the 0th offset. Here's the 9th, 10th, 11th, 12th offset. And so if we take the address of hex and we add 12 to it, we'll find out that the answer is C. And we can just do that. So we could use code like you see over here. EAX is a 32-bit register. We don't want all those bits. And so I will AND it with this F, which masks off the low hex digit, the low nibble. What about the high 32 bits? Well, they're all zeroed out by this operation because I'm setting the low 32 bits. So there's 0 extended. So I basically grab the low nibble of RAX using this instruction. And then that's good because I'm going to add that to hex and go and retrieve the byte at that location and put it in AL, which is the alias for the low 8 bits of RAX. I have to use RAX here. I can't use AL or EAX here because I have to use 64-bit stuff inside these square brackets for an effective address in the 64-bit world. And that will retrieve the correct digit, and then I can go on. So that's one way to do it. Another way to do it is to use these instructions right here, translate and translate byte. And they are the same instruction. It's just yet another Intel-ism. You might write this in your assembly code and see this in the disassembly, or you might have the opposite thing happen. It's fine, they're the same thing. This instruction will look up a byte in a table pointed to by RBX. So RBX is an implicit argument to this instruction. And it's going to load that byte into AL. So another implicit. You're not going to say, translate and give it a bunch of registers. You're just going to have this instruction by itself. And then you have to know that it's going to use RBX and RAX in this way. And what does it do? It effectively does this, the thing we just looked at on the previous page. It takes RBX, it adds AL to it. It puts at this address and puts it in AL. And you can't actually do this. This is not an instruction that will assemble. You should try it and see. I always advocate trying stuff that doesn't work, because then you'll learn what the error message looks like when that thing doesn't work. So the next time you see that error message, you'll know what's going wrong. So in this case, it won't work because this is a 64-bit register, but this is 8 bits, and so it won't let you do this. It'll complain. But this is effectively what it does. And let's see how it does it. So here's my RBX here. Here's my RAX over here. And the first thing I do is I'm going to peel off the low 8 bits, right? The alias for that is AL. And I'm going to take that and add it to RBX, which gives me the address, 2133. So RBX at 2130 is pointing here at this little array. And 2133 is going to point down here to this cell, which holds D. So we'd go to that cell, we grab the D that's there, and we load it into AL. Right, D is hex 44, and so we see 44 in here. And notice that this stuff up here didn't change. Right, AL got modified, but the rest of it didn't. And so now we have this in AL, and that's how translate works. That's all it does. It grabs the address in RBX, adds AL to it, fetches the byte at that location, and puts it back in AL. It runs pretty fast. If you're doing lots of lookups with respect to a single table, and that table is aligned, this is going to be a really fast way to do some translations, because the entire table is going to be in cache. How can I say that? Well, if your table is aligned, I can only have a table of 256 values, because that's all that AL lets me index. And so a page on Linux is 4K, and 256 bytes is significantly less than 4K. So the whole thing is going to fit into a page. It's going to be in the fastest cache possible, and this is going to run really quickly. The one wrinkle to using translate this way is that it's a callee saved register, which means when you're going to do this, you need to save RBX and then restore it at the end if you are worried about your caller. If you want to preserve that for your caller. If you want your caller to potentially crash, then don't worry about it. And maybe your caller will go off into the weeds and you'll seg fault. And you'll wonder why you're seg faulting. And it'll be because you didn't save RBX. All right, so let's use it. Let's use it in a program, right? This is like when you learn a new word, you want to use it in a sentence. You learn a new instruction, you want to use it in a piece of code. And the hello world of assembly is really converting to hex. That's really what you run into a lot. The printing a value as decimal is another fun one, but we're not going to dig into that too much. It turns out to have some nasty tricks to make that work fast. So here we go. Here's my little prthex.asm, and it's just a little assembly file. I don't have a little build thing at the top because this is not going to build by itself. We'll see the next piece that actually uses it in a moment. But let's just focus on this routine. Got a text section up here, and here's my print hex. Here's my label for the top of it, and notice what I do. I push RBP, and I put RSP in RBP, and then I push RBX twice. So why am I pushing RBX twice? Well, I push it once because I want to save it, and I push it the second time because I want the stack to be aligned. So remember, the stack is unaligned right here, and then I push RBP, And now the stack is aligned on a 16-byte boundary. And then I push RBX, and now it's not, right? It's off by 8. And so if I push RBX again, now the stack is aligned again on an 8-byte boundary, and life is good. I could have done something else here, like and RSP with -16, that would work. But this is a single byte instruction, and so that's what I'm going to do. Push RBX, and life's good. Load effective address. I'm going to go ahead and grab the address of hex and put it in RBX, right? This is going to be the base of our array. And what is it, hex? Well, that's my little hexadecimal character array. And it's in the data section. So it's in our initialized data. Then I take RDI and move it into RSI. What the heck? Why am I doing that? What is RDI? I didn't mention it up here. Well, RDI, if you remember, is the first argument to a function according to the calling convention. And I didn't tell you how many arguments or what they were for it, but I take one argument and it's going to be in the first argument and it's going to be an RDI as per the calling convention. And so I just copy that into RSI. Why am I doing that? We'll see in a minute. So then I take buffer and I load that into RDI. So I got RDI, which is my argument. I put it in RSI to save it. And now I load buffer into RDI. And really, I can explain why pretty simply. RSI is the source register, the source index register, and RDI is the destination index register. I'm not going to do string commands in here, but it's conceptually easier for me to remember as I'm writing code that the source of the bytes is in here and the destination where I'm writing the result is in here. It just makes it easier for me to keep track of what I'm doing. And what's my destination? It's this thing called buffer. What is buffer? Well, it's 17 bytes reserved in the BSS section. That's my uninitialized data section. I reserved 17 bytes, label for that as buffer, and I put that in RDI. So I'm going to pull from here and write to here. Okay, well, this is going to hold a 64-bit value that I want to print out in hex. So how am I going to do that? Well, we'll see that in a moment. But remember, RSI holds the value I want to print out in hex. I'm going to zero out EAX. And then I'm going to put 16 into ECX. So I zeroed EAX. I moved 16 into my count register. That's because I'm going to print 16 hex characters. And I'm going to use ECX to enable me to do that using the loop instruction down here. All right, there we go. That's my setup. Now I take 0 and I move that into RDI plus RCX. What is that? Well, RDI holds the address of buffer. RCI holds 16, and I put a 0 there. So I'm going to null terminate this guy. All right. Now, here we go. I go ahead and take SIL. What is SIL? SIL is the low 8 bits of RSI. In case you've forgotten that, right? I can address, so RSI is the full 64 bits, ESI is the low 32, SI is the low 16, and then SIL is the low 8. So I take the low 8 bits of it, and I put that in AL, which is the low 8 bits of RAX. And I've already set it to 0 up here, so this sets it in here. Then I AND AL with F to mask off the low nibble. And so now AL holds a value from 0 to 16 based on the low nibble of what was in RSI, which is the thing I'm trying to print. And then I call xlate. Okay, so translate is going to take RBX, which is an unchanging pointer to hex, points to here. And I'm going to add what I got when I masked off the low 4 bits of this. So I'm going to find the correct hex digit for that. And that's now going to be in AL. And so now my task is put AL into the correct slot in buffer. What is the correct slot going to be? Well, it's going to be this. RDI plus RCX minus 1. And I'm going to put it in there. That is some craziness. Why is it minus 1? Well, I started with it at 16, and I put the null terminator there. So I want this to go at byte 15, right? I'm going to always be off by 1 because RCX is decremented here at the end. So when it's 1, I'll put it in the 0th position. And then my loop will decrement RCX, which will be 0 and terminate. So that's just a little bit of weirdness there. So if you want about 16, that's the right value. And this minus 1 is also correct. You got to watch this stuff because RCX is basically a loop where the base is 1 instead of 0, right? Because as soon as I go through with 1 and decrement and hit 0, I terminate. I don't go through it again with RCX equal to 0. All right. So I store this in the correct place in the buffer. And remember, I'm pulling the low. So picture this in your head. I'm pulling the low 4 bits off, finding the correct way to encode that in hex, and then putting that in the buffer. And so I'm filling the buffer from right to left. So I'm filling it from a high address to a low address. And that works well since this is going to count backwards. All right, there's the next thing I do is I shift RSI, which is the thing I'm printing, right by 4 bits. So the 4 bits I pulled off, they fall off into the bit bucket. And now I'm in the position that when I go in the loop again, I take the low 8 bits, put them in AL, mask off the low 4 bits, and then find the next one. And then I drop those 4 and continue around until I've done this 16 times. I count from 16 down to 1, and then I decrement and fall through. Whew. So that will fill my buffer with the hex value for my argument. And then I want to print this out. So I take buffer, I put it in RDI, which is I had been using up here to point to buffer, but I don't need it anymore. I can just use buffer for that now. So I put that in RDI, and that's the first argument to put S. And so I call put S with respect to the PLT. I then pop RBX. Remember, I pushed it up here. In fact, I pushed it twice, but I just pop it once. I restore it. What happened with the other pop? Is that going to be a problem? No, it's not going to be a problem because the leave instruction is going to restore the stack pointer to its initial state. And so it won't matter that I never popped it, right? The stack pointer is going to be explicitly set back to where it was. So it's effectively going to pop it for me. That should make sense to you. So I'm going to do that. That restores the stack pointer. That restores RBP as well. And then I return. And I could have had the other 2 commands here and it still wouldn't have mattered, right? This is the same as move RSP, RBP, and pop RBP. And that would still have fixed the stack pointer and popped RBP. So there you go. So that's going to take care of that. I don't need the extra pop and won't even have it. And that is my little piece of code that will print a 64-bit hex value provided in RDI, has no return value, and there you go. Whew. So how do I call this? Well, here's some code to actually call it. And so here we actually do have a make line. And you notice I'm going to assemble it, and then I'm going to dynamically link it with the C library because that seems like a good thing to do. So I have a global start, and there's my start down here. I set everything to default relative addressing. I declare put S to be external, which I'm going to need because this code is going to explicitly call put S. And then I include print hex.asm. So that just goes and it's just like pound include in C. It's going to grab the program text, it's going to grab the content of that file and paste it in right here. And then I say section text. It's always a good idea when you're starting to write code to say section text, because if I didn't, I'd be in trouble, right? This gets pasted directly into the file, and the section I'm in right now is BSS. And so I would be trying to add instructions to BSS, and the assembler would bark at me and tell me I can't do that. And that's a pretty cryptic thing to tell me. So I don't want to see that cryptic instruction. So I just put section.text right here to avoid that problem. And now my instructions are in a text section. And where do they go in the text section? They will go right after this, right? If this is accumulated in the text section, and then these instructions for the next piece will go right after this return, or maybe aligned somewhere there. And I put a value to print in RDI. There's my value. I call print hex, which is my little routine to print it. And then I terminate. I put 60 in EAX. I zero out EDI with the return value. I do a syscall and a return. There's my immediately terminate the process. And that's it. And there's a chance I have that code lying around over here. Let's see if I do. There we go. And I do. So let's go ahead and there's hex test. There's print hex. And so I should be able to just say make hex test asm, and it does, right? And so you see what it does is it just calls the assembler, outputs a .o file, then it calls the linker with the little dynamic linker specified, and it outputs hex test, linking it with the C library. I run hex test, and I get exactly the output I expect, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 0, which is precisely what I wanted to print. And I could change this and print different stuff. So I hope that all made sense to you. Let's see. Is translate used? It turns out it is used. I grabbed a few libraries where I thought it might be used and did a count of how many times it occurs in those libraries, and it's not 0. There are several little routines in the JavaScript core, in the G and utils. There's a bunch of them in libcrypto. I was wanting to go look at a few other crypto libraries, which I expect do in fact have them in there, but there were a lot of instances of it in there. Blender had a few. What else did it have? A few things that do some sound stuff. I ran it on gcrypt just for fun. I found 2 in there. I ran it on the Qt engine, found 18 in there. I ran it on WebKit for kicks, and found 1 in there. So all the programs that I ran it on, I found it, but I was choosing programs I thought might contain it. So it's definitely out there. You will run across it. It's weirdly enough one of those little things that shows up, that used to at least, maybe still does. I don't know. I haven't looked at a huge amount of modern malware, but it showed up a lot in malware, at least when I was looking at it, in weird use cases and just bizarre things that were being done. And sometimes it's interesting to go and see how many times these things are used. And so I've got a script that I run sometimes that goes and looks for mnemonics and counts them on a freshly installed Linux system. And just see how many times they're out there. sfence is 1, has to do with parallelizing stuff. Shows a bunch of files. This one's a great one. I always liked this one. I always look for this. So this is, for some reason, an opcode that I remember, I think because it's pathological, right? Mnemonic is intended to be a memory device to help you remember something. And this is the mnemonic for an instruction on the x86. I'm not gonna tell you what it is. You can look it up. I will tell you it has to do with arrays. And I just find this to be absolutely just delightful. And it shows up in weird places. The point of this is you have some instructions that are favored by some compilers, and you have some instructions that are not favored. And right, I mean, the fact that an instruction exists on the machine doesn't mean you're going to see it in a lot of pieces of code, unless the compiler writers decide that they want to make use of it, and they don't always have to. In fact, I'm modifying the slides for next time to cover a case of using a very limited set of instructions on the x86. So we'll talk about that next time. But some instructions are favored by them and some are not favored. And lots of instructions do some pretty specialized stuff. And if you're writing code that tries to analyze this stuff, you have to be able to deal with this wide and almost pathological set of instructions. All right. They've moved on to the next piece of the next area of the roof. And so I'm getting some noise here. Hopefully it's not making its way through. Points to analysis. Let's go back to that. So if you remember that the purpose of this was, we've got a program. The program is going to have pointers. I would like to know what points to what, or what might point to what. And Steensgaard claims to have a fast algorithm that can do this without me having to worry about control flow, and that would be awesome. So he gives you a little C-like language, which here's an example of it over here. And he gives you a set of types, right? The purpose of one of the main purposes of his algorithm is to do this assignment of types. So here are the variables in the program: A, B, X, Y, P, Z, C, all those over here. Each one has an associated type. And then I see what I can figure out about that type. And so you can see here that tau1, which is the type for A, looks like a reference to a tau4. Tau4 is the type for X, which is bottom. So it's by the way, these ordered pairs, these are the you sort of think of those as the types for a data object in memory, and these as the types for an associated function. And we're not dealing with that right now, so we're leaving all those as bottom. So we can also construct from that a graph. Here's a graph. How did I get this graph over here? I said A points to X. Well, sure. A is tau1, which is a reference to a tau4, which is an X. Why does it also say Z in here? Z is also a tau4. Okay, so there we go. X and Z. And Y as well? Sure. Y is tau5, which is a reference to a tau4, which is Z and X. And so I could build this little graph over here. P stands alone. And this is an example straight out of Steensgaard's paper. He gives you this and he says, here's an example program, a typing that obeys the typing rules. He's not claiming this is the only way to assign types, right? Maybe I can do something much more specific or a little different, but this is a typing that obeys the typing rules. And the graphical representation of the storage shape. Here's what a storage shape graph is. That's what he means by it. Now, the variables X and Z are described by the same type. Now, he points out that T1 and T5, I think I have that called out. Yep, T1 and T5. T1 is a reference to a tau4, and T5 is a reference to a tau4. They are structurally equivalent, okay? Structurally equivalent, right? They're both references to the same type. And T2 and T3 are both references to the same type, a tau5, okay? But we don't require them to be the same type, right? We don't require that tau2 and tau3 be equal. We just note that they are references to the same type. And that gets back to what he was talking about. We were talking about in the previous class of over constraining. We don't want these to have to be the same, because in your program, there could be many places where you've got a data structure that's a reference to, let's say, an image that's stored in memory. And those don't have to be the same type, right? You have different types for those. So they're not considered the same type. Also, T4 and T6 are both primitives, but we don't know what they are. All right. So let's think about this for a minute. Could we apply this to assembly? Up here, it kind of made sense, right? We have variables, we have storage locations, we have types. In assembly, how would we apply something like this, right? Are the registers variables? Are locations in memory variables? Are locations, are they both? Should we think of both of them as variables, as neither? Okay. Can we think of a register or a location in memory as having some associated type? Does that make sense? They're just bags of bits. Well, the program, the C program, is just bags of bits, right? A is going to be something like, well, in this case, a pointer, right? A holds the address of X. We can assume A is a pointer. So A is going to be a 64-bit thing. And so is B. What about X and Y? Who knows? Maybe they're ints and 32 bits. Maybe there's something else. We don't know. So yeah, I think this maps on it pretty well. You just have to think about what's happening. So back to Steensgaard's algorithm. He gives you an algorithm for going through his little program and figuring out what points to what. The basic principle of the algorithm is that we start with the assumption that all variables are described by different types, different type variables, and then we try to merge types as necessary to ensure the well-typedness of different parts of the program. So we go back. We might start out with all of the variables here and just give them tau 1, 2, 3, 4, 5, 6, and 7. We could have done it that way. And they would all have different types. And then over time, we would learn that we could merge certain types like X and Z and make that change. All right, so step one, it's pretty easy. Start with the assumption that all variables are described by different types. That sounds like a thing I would know how to do, right? I'll just write down a different variable name for each type of each variable. Done. Phase two is a little trickier. Merge types as necessary to ensure well-typedness. That's harder for me to grok. And before I get into the specific mathy details of what he means by that, because he does, I think it is worth going through an example of applying the algorithm. Even though we don't fully understand what the algorithm is just yet, I think it's worth going through it now to get a sense of what we're trying to do, to make that more concrete. And that, I think, will then motivate the discussion of the mathy parts later. Before we get into that, though, we have to talk about one thing he mentions, because you may not be familiar with it, and if you're not, you probably should be. It shows up everywhere. And that is what he calls a union-find data structure. Sometimes it's called a disjoint set data structure. And it's a data structure that keeps track of a partition of a set of elements. And in this case, type variables. So blocks of the partition can be combined pretty quickly with a union. For example, up here, I have a partition of the digits 1 through 5. This is a block that contains a single digit. This is a block that contains a single digit. This is a block that contains a single digit. This is a block that contains 2 digits. The partition consists of these 4 blocks, 4 non-empty blocks, and that is a partition of the entire set 1, 2, 3, 4, 5. Okay. Another way to think about it is each of these is an equivalence class. Okay, on the set. So 1 is equivalent to itself, 2 is equivalent to itself, 4 and 5 are equivalent to each other and themselves. All right. partition, equivalence class, however you'd prefer to think about it, that's fine. Union is a fast operation. So if I take the block 2 and the block 4, 5, I can merge those and wind up with this new partition down here. 1 in a block by itself, 2, 4, and 5 in a block, and then 3 in a block. And this is a fast operation in this data structure. It's also fast to check whether 2 elements are in the same set. It's a find operation. So if I said 1 and 2, it would really quickly tell me no. If I said 4 and 5, it would really quickly tell me yes. So it's fast for me to check the equivalence of 2 objects. Okay. Initially, each variable is its own equivalence class or a block of a partition, however you want to think about it. If 2 variables we decide are the same, then we're going to merge their equivalence classes. So this is how we're going to use it, right? And it makes sense. If our goal is to be merging these type variables, we'll keep them in these equivalence classes, and we'll do it that way. This is an aside. Union find data structures are interesting in themselves. They show up all over the place. They show up in game software. They show up in database software. It shows up all over the place. If you use some clever stuff, you can get the operation down to a really, really, really fast operation. And it has to do with something called the inverse Ackermann function. And I like this. This function, the inverse Ackermann function, has a value less than 5 for any n. So right, as the problem grows, as n grows, n's the size of the things we're talking about. As n grows, this gets larger, and it gets larger without any real bound, but it's less than 5 for any value of n that can be written in this physical universe. So the disjoint set operations take place in essentially constant time. Okay, it's possible for a value greater than 5. It's possible greater than a billion. It's going to take an n that is so large that it has no practical value. We will never achieve it. So it's effectively a constant time operation, and I just find that to be a really neat property of this. The Ackermann function itself. This is further aside. I'm probably boring you, but I find this interesting stuff. The Ackermann function, if you're not familiar with it, is also fascinating. It turns out it's the first function that sort of proves that you can have a computable function, a total computable function that is not primitive recursive. What does primitive recursive mean? A function is primitive recursive if you can convert your recursive program to a program that uses for loops. That's the best way I can think of to say it. And the Ackermann function is not. And the way you show that it's not is you show that it grows faster than its value grows faster than any function that could be primitive recursive. It's a really cool proof. You have to just take my word for it or go look it up. So primitive recursive functions constitute the PR complexity class. There's tons of complexity classes. And the Ackermann function is not in that class, but it is computable. So that's kind of neat. It has a lot of so I say Ackermann function. There actually are a lot of different variations of the Ackermann function, but most of them have a really simple, deceptively simple recursive definition, like A of, and typically there are 2 parameters, A of m and n is equal to A of m minus 1 and n minus 1, something like that. And then there are tricks when there's 0. It turns out that these things grow in this really sort of pathological way, and they're fun to play with. So you'll rapidly exceed the ability of your machine trying to compute these. All right, enough of that. We're way off in the weeds on that. Union find data structure. We're going to store stuff in a fancy kind of array. So we're going to apply the 2-phase method we talked about to the program over here on the right. There it is. not a super complicated program. In fact, this one we've already looked at. And we'll need a typing rule. And the typing rule that we'll need is one that addresses these kinds of statements. And if you ignore the control flow stuff, which Steensgaard claims we can, then every single statement in this program is of the form a some variable gets the address of another variable. Every single one is of this form, right? And so look at here. This is well typed if, by some typing rule A, this is well typed if these things hold, right? X is a reference to tau and Y is of type tau. And that makes sense, right? If Y is of type tau, right, type tau, this means that X is going to be a reference to something of type tau. So that is what we'll have. And so this will tell us how to assign types to things. So phase one says everybody gets their own type. Done. So here are the variables in the program. There are 7 of them, A, B, C, X, Y, Z, and P. And they all get their own type. Tau 1, 2, 3, 4, 5, 6, and 7. And initially, I just say, you know what? It's a reference to some primitive thing. That's it. I don't know anything else about it. Maybe I'll learn something new as I go along, but for right now, no. And the way to think about the union find part of this is every one of these is in their own individual equivalence class or individual block of the partition, right? My collection of 7 variables is partitioned into 7 blocks, 1 variable in each. So we're going to process each statement of the program exactly once. So it's going to be fast to go through it. And if 2 type variables have to be joined, we'll join them. We won't consider function pointers, so we'll never use the second element of this ordered pair. This is discussed in the paper, but for simplicity, we just won't do that here. If the left-hand side type is bottom, then we won't need to join. And we'll see that. If the left-hand side type is not bottom, then the 2 types must be joined, and we'll see that. So let's just get into it. Ooh, look at this. Look at this. Some nastiness has happened here. Sorry about that. Not sure why that occurred, but there we go. There's a tau 1 sitting there and a tau 4 sitting here on top of the X. So A holds a reference to X. There we go. And so the type of A, which is tau 1, should be a reference to the type of X. And what's the type of X? It's tau 4. And so what we should see is, based on this rule, we should go ahead and make this into a reference to a tau 4. All right, so we know these 2 things. And there we go. So we replace it with this. This side was bottom, so we can go ahead and do that. If this had something else here, we would have had to merge those types. We'll come back to an example of that. But for right now, since they were both bottom, we can just replace that with tau 4. That satisfies what Steensgaard wants. And then we update the type for A, which is over here. And there we go. So now we've gone through the first line of the program and made a change to our type. Nothing has been merged yet. So far, that's all we got. B holds a reference to Y. So the type of B must be a reference to the type of Y. B is tau 2, Y is tau 5. So we're going to replace this line with this line, making B a reference to tau 5. Third one, Y is a reference to Z. Exact same logic applies, and we make the change. Now we're on this line. Y gets a reference to X. So at this point, Y, tau 5, is a reference to tau 6, which is Z. We picked that up from here. We also want it to be a reference to X, and X is tau 4. So now we have this pair of things. Okay, the left-hand side of this pair is not bottom, it's tau 6. And so we have to merge the two type variables, tau6 and tau4. Okay, so what does that mean to merge them? All right, we're going to merge them in the sense that I had this set, this union find set, and I'm going to merge tau4 and tau6. And so there's an algorithm for it in the paper, but for now, let's just replace one with the other throughout. So what does that mean? That means I'm going to replace, let's say, I think tau6s with tau4s maybe. And so I'll make this change. Yep, tau6s get replaced with tau4s. And there we go. Now it looks like this, right? Now it's a tau4 in here. This tau6 is now a tau4. So I just replaced them all the way through. And you can see that, in fact, I now have two things that are equivalent. All right, C holds a reference to Y. So the type of C must be reference to the type of Y. What's the type of C? Oh, look at there, it's bottom in the left-hand side. So great, we can just plug that in and we're done. We have finished all the work we needed to do under the Steensgaard algorithm. And we wind up with this set of typing, which gives us this graph. Okay, and so believe it or not, we've discovered what points to what, right? Tau2 and tau3 point to something of type tau5. Tau1 and tau5 both point to something of type tau4, and tau7 is off doing its own thing. And there you go. We don't know how to relate this to the other ones. Maybe it does relate. Maybe tau7 turns out to be in some way related to one of these, but we didn't have information in the program that let us conclude that. And remember, we are choosing we're not necessarily choosing the strongest solution, right? We're choosing the weakest solution based on what we know. And there we go. So we've gone through the two phases of the Steensgaard algorithm and concluded with that. We could use variables in here. That is maybe a little bit nicer because now what I know is that B and C point to Y, A and Y can point to X and Z. Does A point to X? Does A point to Z? How about Y? They could, right? They could do this. Not necessarily the case that there were a time when A holds a pointer to the same thing that's held in X. Not guaranteed. Does it make sense given the original program? Let's see. So A can certainly point to what's in X. B can point to what's in Y. We got that. Y can point to what's in Z, sure. Y can also point to what's in X, okay? And Z can point to what's in Y. So yeah, it does make sense. For this little toy example, all this stuff seems to work out pretty well. Note, we have concluded that X and Z have to have the same type. That's a pretty strong conclusion. There's nothing in the program that necessarily requires it. It's just something that we concluded based on Steensgaard's algorithm. All right. Whew. That's all the Steensgaard I have time for today.